Good afternoon and welcome to the 20th annual exhibit of hydrogen and fuel cell technology. We've been here for quite some time talking about the fuel cell technology innovations, the hydrogen technology innovations, and we've added batteries to the mix. One of the important questions we're facing right now in Germany is what to do with the fluctuation in the production of energy. We have renewables, but storage is always an issue. And one of the potential solutions, of course, is electrolysis. We have a specialist in this field who's going to be discussing with me PEM electrolysis on a large scale. He's Jürgen Mergel, head of electrolysis department at Forschungszentrum Jülich. Please welcome with me Jürgen Mergel. Hello. So before we jump into the very important topic, could we have a short, broader picture? Jülich, of course, plays a fundamental role in research, development, and you've been involved in the fuel cell industry and the electrolysis aspect for a long time. Could you describe overall the activities at Jülich?
Okay, so Jülich is one of the greatest research centers funded by the German government in Germany. More than 5,000 people are working in Jülich on different topics. And in the energy field, our institute, Electrochemical Institute, Electrochemical Process in Engineering, is involved in fuel cell development, in solid oxide fuel cells, in direct methanol fuel cells, and also in high temperature fuel cells. And in the past we had large activities also in the electrolysis, especially in the alkaline electrolysis in the early 80s of the last century. And after the decision of the German government to go more into renewables, the interest of electrolysis is growing very fast here in Germany, and therefore it decided our institute, while we have a big background in fuel cell development, especially PEM, that we will go in the development of PEM electrolysis.
Okay, we could do sort of a two-sided discussion here. One is the very basic question. We want to take all the audience with us.
Yeah.
A non-technical definition of what electrolysis is.
So electrolysis is very simple. This is the decomposition of water into hydrogen and oxygen by electricity. So that means this is the transformation of electric power into chemical power.
Okay, that's wonderful. Now we've got that basis. Of course, there's a number of technology potentials there. How do we use this? You know, some people prefer one technology, some people prefer another. You've worked with both.
Yes.
And of course, I'm referring to not simply PEM. So perhaps we could discuss not specifically your current developments, but on a broader scale, what are the advantages and disadvantages of the various types of electrolysis?
Okay, so we have at the moment three different technologies. The oldest one is the alkaline electrolysis. This was developed in the, let me say, early, this was in the beginning of the 20th century. This is a well-developed technology. You use KOH as an electrolyte. Current densities are in the range of, let me say, 200 to 400 milliamps per square centimeter. It's operating very well. The durability or long life is around 60,000 hours or 80,000 hours. That means this kind of electrolysis works very well about 10 years, 20 years. And the PEM technology, was developed from General Electric in the 70s of the last century. So this is a technique which is around 40 years old. And this technique in the late 80s, so this was not founded, and while it is very expensive, so it goes a little bit down with the development of PEM, and also normally hydrogen could be cheaper made out of natural gas than out of electricity. And therefore the interest in electrolysis was very, very small in the past. But the advantages of the PEM electrolysis that you have very high current densities. If you compare this to the alkaline water electrolysis, that means if you have, let me say, area of this paper, this is around 300 square centimeters. In alkaline water electrolysis, you will have 60 amps or 100 amps. In a PEM electrolysis, you can produce hydrogen with, for this kind of cell area with 300, 400, 600 amps per this unit. That means with a very high current density, and that means your stack will be smaller for PEM than for an alkaline electrolysis, and therefore the footprint is very small for PEM electrolysis if you compare this with an alkaline electrolysis. One drawback is the investment costs. So depending on the electrolyte you use, this is a protonic conductive membrane. So this is an acid media. You couldn't use only precious metals for the electrodes. And as you know, platinum, iridium, these are very expensive materials. And therefore, I think we must develop cheaper electrolysis units as are now commercial available.
We'll get to the specific issue of how to make them cheaper, because that was where your innovation is. But just on the general question again, I understand how important this can be to reduce the footprint. We've had this issue before in fueling stations. If you try to put a fueling station for hydrogen next or on a gas station, they're worried about every square foot. They make more money from their car wash stuff, and the big the financial gain for the person who runs the car wash is actually the store that sells the chocolate bars. It's not the money they make selling gas, and they don't want to have a large space lost.
That's right.
And if we consider on-site production of hydrogen, that is an issue. But there are other issues. For example, if we are trying to recover excess energy within the grid, which can fluctuate dramatically, or if we're trying to recover the energy the grid cannot absorb from renewable sources, we could take a wind turbine, it starts to turn, and right now there's this huge debate. People almost don't like wind turbines because they hear we don't need them. Sure, we need them, but we have to develop technologies to absorb that energy when it's not being used and to feed it back into the grid when it's being used. So the question is the comparison between PEM technology and alkaline technology. Can alkaline technology respond as quickly to these fluctuations?
Yes. So we have operated an alkaline electrolysis in direct coupling with a PV field for many years, for 10 years. And I think, this is my personal opinion, PEM and also alkaline electrolysis are very dynamically. Okay. I think one advantage of the PEM is that you can run a PEM from 10% partial load up to 200 or 300% of the nominal load. An alkaline electrolysis, you can run only 20, 40% of partial load up to 100% or 150% of nominal load. And this is one advantage of the PEM, that you can run a PEM electrolysis in a wide power range.
Even the excess power doesn't present a challenge, destructive challenge to the cell. That's very interesting. Of course, very important, because initially we may not have enough of the PEM cells connected up. They can deal with the overload, and we could add to the extent they become financially profitable. And we are talking about profitable technology. Let's now deal with the specific developments here because you mentioned the material costs, there are precious metals.
Yes.
And that is a fundamental barrier to mass scale production of these units as for the PEM technology in general. And the second issue is the energy density issue. So on both levels, you've done a lot of thinking and you've come up with a very specific approach to optimizing PEM electrolysis. Please describe that innovation.
Okay, so what we have done was in the past we have made a cost analysis of the alkaline electrolysis and also of the PEM electrolysis. And at the moment, if you would like to buy a megawatt scale electrolysis for the alkaline, it takes around 1,000 euro for 1 kilowatt in installed capacity. If you would like to buy a PEM electrolysis state of the art, it costs around, let me say, 2,500 euros per kilowatt in installed capacity. And this is only for PEM electrolysis who work at a current density of 1 amp per square centimeter. If you increase the current density by a factor of 2, that means you run your PEM electrolysis at 2 amps per square centimeter at the same cell voltage, the same efficiency. You can reduce, so that was our calculation or simulation, you can reduce the costs by a factor of 2, not quite 2, to 1,200 euros per kilowatt. And what we also found is if you reduce the catalyst loading by a factor of 10, so this is a very high goal. So normally, I do not know, there are some guys from hydrogenics, I thought the normal loading in a PEM electrolysis on the anode side is between 2 and 4 milligrams iridium, and on the cathode around 1 milligram. And this is very high loading and very cost intensive. And if you reduce this by a factor of 10 and you reduce also the high costs of titanium inside the stack, which is needed for the separator plates and current collectors, we found that you can reduce the cost in 2030 down to 500 euros per kilowatt installed capacity. Quite the same as you can do also for the alkaline electrolysis.
So this, I mean, the bottom line there, of course, is this is a potentially massive savings in the cost of energy. Have you also changed factors affecting the lifespan? When you basically you're saying thin is better, the savings obviously in the precious metals, and the fact that energy density is also affected positively. But what about the lifespan of the?
Yes, this is a good question. So one thing is to increase the current density is to go to higher temperatures. At the moment, PEM is working at 60, 65 degrees centigrade. If you go to 80 degrees centigrade, you will increase your power density, but also you will increase your aging effects. And this is a big question. What happens with lower catalyst loading? What happened with higher temperatures? And what happened with the catalyst and with the whole MEA or the whole stack under high dynamic operation? And therefore we have started a project in 2012 to reduce the costs and to study the aging mechanism in a PEM fuel cell under high dynamic load.
I should mention that we are open to questions here. If there's questions from the audience, just raise your hand, and I see one already. Hello, sir.
When you mentioned the cost numbers, what's the production volume you assume?
So the numbers which I mentioned for 2015 was a 1 megawatt unit, 20 units per year. And the number 500 euros per kilowatt, this was in 2030, and this was 200 systems per year in a 3 megawatt scale, 3 to 5.
Do we have any other questions right now? The option is still open. Let's return to the issue we're really addressing here with PEM electrolysis. It is the issue of future of the energy sector in general. With renewables added to the mix, it's a greater and greater challenge. And of course, it's also a shame that energy is wasted right now because there's a lot of baseline production that likes to be above the maximum demand. And all of that excess energy is just being tossed away. It's an incredibly wasteful thing. And finally, we have an energy grid, and the German energy grid, I take my hat off as a North American, I'm from Canada, but you have to say there are areas where blackouts and brownouts are common. This is it's a luxury. It's an incredibly stable grid, but it's still a grid within which about 30% of the energy that goes into the grid winds up getting lost through resistance.
Yeah.
So addressing this issue, we have to return to the way of using PEM technology to store energy and simply ask the question, first of all, of efficiency.
Yeah.
And second of all, what do we do with this hydrogen? Do we convert it to something like a natural gas? What would be your logical preferences for making the optimal use of energy that's just being de facto wasted right now?
Okay, so our vision is the best thing to reduce also the CO2 amount for the emissions is to bring the hydrogen into the automotive sector. That means the conversion from hydrogen into electricity, but only in the automotive sector. Therefore, you can reduce also the amount of CO2 per year. In the meantime, I think the best thing is to inject the hydrogen into natural gas. But from our point of view, it is not so good to make out of the very high cost intensive hydrogen, which is made out of electricity, methane by power to gas, while methane made out of high hydrogen is much more expensive as natural gas. And therefore, our opinion is to make out of the hydrogen electricity, and if possible, in the mobile section.
On that note, though, is there a limit to how much hydrogen you can directly add into the existing natural gas grid? Because if we don't have the capacity, I mean, we don't have the cars yet.
Yes, that's right.
We have the PEM technology. We don't have the fueling station network. The cars are not right on the market right now in the quantity for which this energy could supply it. So in this interim period, where do we go with that hydrogen again?
In the natural gas, I think, or in the chemical industry. So we are thinking about a big project called HYPOS in the eastern part of Germany, where we make with excess energy, electricity or hydrogen, store it in a salt cavern and bring it back to the chemical industries. That means chemical use of hydrogen. But therefore, the hydrogen must be in the cost quite the same as if you make the hydrogen out of natural gas. And normally you get 1 kilogram hydrogen made out of natural gas. It costs you 2 to 3 euros per kilogram. If you did this or do this with electricity at the moment, it costs you 8 to 10 euros per kilogram, and therefore it's very important to increase the efficiency of the electrolysis to decrease the costs of hydrogen made with electricity or made with electricity.
Do we have any questions before we wrap up? Yes, we do. Wonderful.
Thank you. We're just talking about costs and all, and we're always talking about throwing away electricity.
Yeah.
But what sort of money is payable for the electricity? Like if we say wind power or solar power is not for free, we have to integrate it to the market. The whole politic discussion going on at the moment, which means this is not for nothing. It's
That's
actually
right,
priced.
yes.
So if we look at the, let's say, the 20-year scale, which was guaranteed to invest into renewable energies by the EEG before, if we combine that with hydrogen or methane, maybe, is there a price you can estimate what could be paid out of that technology for the electricity?
Yeah, so if you use electricity in electrolysis, the hydrogen cost depends on the price of the electricity. And what we found, so normally the price should be in the range of 4 to 6 euro cent per kilowatt. Then the hydrogen could be in a range of, let me say, 4 euros per kilogram hydrogen.
It's interesting because that's wind power onshore.
Yeah.
I was just saying that's really interesting, that number, because this is the price of wind power onshore.
That's right.
Yeah.
Onshore, yes. But okay.
It's such a complex.
It's without transportation and so on. But I think if you are going to 8 or 10 euro cent, so the hydrogen done by or produced by electrolysis will cost 8 or 10 euros per kilogram.
I would love to continue the discussion, but my colleague Mona Lee is going to shoot me if I don't get off the stage because it's her time. Her slot is approaching. But you can continue the discussion. The booth is C68. It's just over here. It is a very incredible discussion because ultimately, among the prices we pay for energy is energy security and also political stability. We have no real large energy resources within this country, which has a huge demand for energy. So self-sustaining energy security is a fundamental good for the society, and it's a very important issue. So it's, of course, not simply the dollars and cents, but it's the peace of mind. On that note, it has been a pleasure, Jürgen Mergel, to talk with you. It's been a conversation with Jürgen Mergel, head of electrolysis department at Forschungszentrum Jülich. I hope you'll be back here next year to continue the discussion again.
Okay, thank you.
Thank you, Jürgen. And thank you very much.